What's up, everybody? Welcome to another video, and I hope you're ready to flex those brain muscles because this is part 3 of my Precalculus final exam review series. So if you missed part 1 and part 2, that's okay. I'll put links in the description below, and I'll also have the topics that I covered in those videos pop up on the screen here. That way, if you see a topic that you know you need help reviewing, you can go back to that video and get that review help that you need. But for this video, for part 3, we're going to focus a lot on inverse trig functions. So we're going to look at a bunch of different expressions involving inverse trig functions and find the exact values of all those different expressions. Then we're going to move on to a trig function and find the inverse of that trig function, as well as the domain and range of the original function and the inverse function. Then lastly, we're going to solve a bunch of trig equations. So if you want to see the review for yourself, click the link in the description below, 100% free, of course. And what I recommend doing, highly recommend doing, is downloading this and printing it off, or at least pulling out a piece of paper and copying the problems down and trying this on your own first, then coming back to this video and using this video to check your answers and to fill in those gaps in your understanding, to get some clarity on the places you're confused about, right? I think that's going to benefit you a lot more than it would to just sit back and relax and watch this video, or just to copy down what I'm doing as I do it. Because you know what they say, best way to learn math is to do math, so do it. Okay. Last couple of things, I'll put timestamps in the description below so you can hopefully easily find the problems you need help with. And I will go a little bit faster because this is a review video, so I'm assuming that you've been exposed to these topics before, so I'll move a little bit quicker than I normally do. But I already have all of these topics covered in videos on my channel. So if you're finding that you need extra help, go check out my channel, click on the Precalculus playlist, and hopefully you'll get the help that you need. But that's it for the introduction. Let's go ahead and get started. So number 1 is pretty long. It's 12 parts. Sorry about that, but it's all inverse trig stuff, and a lot of students struggle with that. So I figure I'll give a bunch of examples, give y'all plenty of practice. So when dealing with these and finding these exact values, there's a few things you need to have down. So first of all, you need to know how to find basic exact values of just normal trig functions. Like, for example, what is the cosine of pi over 4? What is the sine of pi over 6? What is the cosecant of 4 pi over 3? Those values you need to be able to find. If you don't, go check out one of my videos, figure out how you can find those values, then come back. Because if you can't do that, this is damn near impossible, all right? Second, you have to remember that when dealing with inverse trig functions, our input is a value and our output is an angle. We can expect this exact value to be an angle, right? Just like with regular trig functions, we plug in an angle and get out a value. Inverse does the opposite, right? The inputs and outputs switch. That's how inverse functions work. Third thing we really need to remember, really need to have this down, is the range of these inverse trig functions. Each of these inverse trig functions has a very specific range, and all 6 of them are different. Okay, so the range of cosine inverse is between 0 and pi. So whatever this angle is, we can expect it to be greater than or equal to 0 and less than or equal to pi. Not only can we expect it, but it has to be in that interval, right? So what I like to do is just rewrite this, because asking what's the cosine inverse of 1/2 is like asking cosine of what angle equals 1/2. But remember, that angle has to be between 0 and pi. So where does this happen? Well, let's think. Cosine of some angle equals 1/2. Well, this is positive. So if we're between 0 and pi, 0, pi, somewhere in here, and we're getting out a positive value, that eliminates this second quadrant, right? Because cosine is negative in the second and third quadrant. So that eliminates there. We have already eliminated here. So we've narrowed it down to the first quadrant based on this range of cosine, as well as the fact that this is positive, right? So what angle gives us 1/2? We should know that from the unit circle. It is pi over 3. Took me a second. Sometimes I get them mixed up. Pi over 3. And so that's our theta. Theta equals pi over 3. So 1b is very similar, except this time we're dealing with sine inverse instead of cosine inverse. But the process is pretty much the same, all right? We know that sine inverse takes in values and spits out angles. So we're looking for an angle here. And asking what's the sine inverse of negative root 3 over 2 is the same thing as asking sine of what equals negative root 3 over 2. So we're looking for that angle, but what has to be true about that angle? It has to be within the range of sine inverse, which means that that angle has to be greater than or equal to negative pi over 2 and less than or equal to pi over 2. Make sure you have those ranges down. So we're looking for an angle where when we plug it into the sine function, we get negative root 3 over 2. But we got to make sure that angle falls within this range. So let's draw it out. Here's pi over 2. Here's 0, and here's negative pi over 2. Remember, we start at 0 and we move the opposite direction when we're dealing with these negative angles, all right? So now we can eliminate, right? We can eliminate one of these quadrants based on whether this is positive or negative. It works the same every time. Since sine of what angle equals a negative, we can eliminate which quadrant? The first, right? Because all these angles in the first quadrant give us a positive value for sine. Here we have a negative. So it must be in this fourth quadrant. So it must be between negative pi over 2 and 0. This is the common mistake people make. They see this and they go, oh, negative root 3 over 2, and they pull out their unit circle and they look and they write, oh, the answer is 5 pi over 3, and they write that out. That's not the correct answer. It's not 5 pi over 3, and the reason why is because 5 pi over 3, it is true that the sine of 5 pi over 3 equals negative root 3 over 2, but 5 pi over 3 is not within this restricted range of sine inverse, right? So actually what we have to do is start at 0 and move backwards to negative pi over 3. And that's our theta, is negative pi over 3, not 5 pi over 3. So that's a very common mistake, so if you made it, that's okay. But just make sure to pay close attention to that range of the inverse function that you're dealing with. So 1c, what's the tangent inverse of the square root of 3? Well, same process. We know this is going to give us some angle. I already wrote it out for us here. And we know that asking what's the tangent inverse of root 3 is the same thing as asking the tangent of what angle equals square root of 3. But what do we have to remember? The range of tangent inverse, which is similar to sine, except what's different about it? Negative pi over 2, strictly less than. We disregard the equal because that's where tangent has its asymptotes, right? So less than theta, less than pi over 2. So similar, we just exclude those endpoints. So what we're looking for here is tangent of what angle equals root 3, but remember this angle has to be between negative pi over 2 and pi over 2, okay? So pi over 2, negative pi over 2. Now we can eliminate one of these quadrants based on whether this is positive or negative, right? We have a positive here, so what does that mean? It means we're in the first quadrant. We can eliminate this fourth quadrant because tangent is negative in the second and fourth quadrant. So it definitely can't be in this fourth quadrant. So we've isolated this theta to somewhere between 0 and pi over 2. Now we just have to find out what value for theta this is. So I personally have this memorized. I know it's pi over 3, but if you don't have this memorized, I'll show a quick little trick, something you can do. You can draw a triangle, and you can say, well, this is the angle theta, right there. And you can say, well, tangent is, let's see, SOHCAHTOA, opposite over adjacent. So that means the opposite of this angle is root 3, and the adjacent is 1, because square root of 3 is the same thing as square root of 3 over 1, right? So then you can use Pythagorean theorem to solve for this side. You're going to take root 3 squared, add it to 1 squared, and that equals this side squared. And when you do that, you're going to get 2. I'm doing it pretty quickly because I just want to show y'all how this works, just in case you don't have this memorized. But I really recommend you have at least the values for tangent memorized like this. Now you can look at this and say, well, whatever this angle is, the sine of this angle must be opposite over hypotenuse, root 3 over 2. And the cosine of this angle must be 1 over 2. And hopefully you know those values, right? And we know that those values happen when theta is pi over 3. So therefore our theta in this case, where should I write this? Theta equals pi over 3. So I just wanted to show that for people who really hate memorizing. But if you do this enough, you eventually will memorize these. But theta equals pi over 3. All right, so now we're getting into the real fun stuff, which are these composition of inverse trig and trig kind of problems. These come up a lot in pre-calculus, so make sure you practice a ton of these examples if you're taking pre-calculus. But let's go ahead and get started. Sine of pi over 4. Remember, sine takes in an angle and spits out a value. So this whole thing is a value. And we're taking the sine inverse of that value, which is going to give us an angle, right? Inverse trig always gives us angles. Remember that. So we're expecting some angle as our solution to this. What else do we notice? Well, the sine of pi over 4, we know what that is. That's on the unit circle in the first quadrant, right? We know what that is. So we can rewrite this. This is the same thing as saying the sine inverse of root 2 over 2, right? That's the sine of pi over 4, is root 2 over 2. Okay? Now we can use the properties of inverse functions. We can switch the input and the output and get rid of the inverse. So this is the same thing as asking the sine of what angle equals root 2 over 2, but what's special about that angle? Remember, it has to be in the range of inverse sine. So it has to be greater than or equal to negative pi over 2 and less than or equal to pi over 2, okay? Has to be within that range. So what angle makes that happen? Well, let's see. This is negative pi over 2. This is pi over 2. This is a positive value. We know that sine is positive in the first and second quadrant, but since we're just looking at the first and fourth quadrant, we know we're limited to this first quadrant. So we can eliminate all these places here. We're in the first quadrant, and we know that our reference angle that works here is pi over 4. So theta is going to equal pi over 4, right? Theta equals. So what do you notice about our answer? It's the same as this original angle, right? And this is something that I really want to point out. When you have the sine inverse of the sine of some angle, if that angle is already in the range of sine inverse, then that's going to be your answer every single time, right? And maybe you noticed that right off the bat and you were like, why is he doing all this extra work? Well, I wanted to do this work to show that it does work out this way, but then I wanted to show the shortcut at the end, that if you notice that this angle is already within the range of whatever inverse trig function is on the outside, then that's going to be your answer, okay? The only issue where we really do have to do all this work is when we know that that angle is not within the range, which we're going to see in the next example, but hopefully that makes sense. So in this problem, you can see that the angle in this inner function is not within the range of sine inverse, right? So we can't just say that our answer is 5 pi over 3 because our answer can't be 5 pi over 3. Our answer has to be within this interval, right? So this is where we really do have to do a little bit of extra work. But the good thing is we know what the sine of 5 pi over 3 is. 5 pi over 3 is an angle we're familiar with. It's on the unit circle, right? So we should be able to find that, and then we can simplify this a little bit. So the sine inverse of, let's see, what's the sine of 5 pi over 3? 5 pi over 3 is in the fourth quadrant. It's going to be right about here. So it's going to be a negative, whatever it is, right? Fourth quadrant. And let's see, our reference angle is pi over 3. So it's going to be negative root 3 over 2. Okay, so this is like asking, what's the sine inverse of negative root 3 over 2? Which is the same thing as asking the sine of what angle, and remember that angle has to be within that range, within that interval, equals negative root 3 over 2. So we have to be between negative pi over 2 and pi over 2. So let's draw a picture here. This is negative pi over 2. This is pi over 2. We have to be somewhere in here. And again, we can always eliminate a quadrant and get down to one quadrant by just looking at whether this is positive or negative. Notice I've been doing that. This is negative, so we're definitely not in the first quadrant. We have to be down here somewhere between negative pi over 2 and 0, right? So we know our reference angle that gives us these root 3 over 2 type values when we're dealing with sine is pi over 3. So we just take pi over 3 and we move backwards. So our theta is negative pi over 3. Don't make the mistake of saying 5 pi over 3. Please don't do it. That's the most common mistake with these kinds of problems. Remember, always check at the end and make sure whatever angle you get as your solution falls within the interval for whatever inverse trig function you're dealing with. So in this case, we have theta. Let's see, where should I write the answer? I'll write it here. Theta equals negative pi over 3. So now it's getting even more tricky because not only is the angle in this inner function outside of the range of sine inverse, but now it's an angle that we aren't even familiar with. We don't know what the sine of 7 pi over 5 is. It's not on the unit circle. We need to use a calculator to find it, but we're still being asked to solve this problem without a calculator. And the cool thing is we can do it, and we can actually find this angle theta without ever even having to find out what the sine of 7 pi over 5 is, and that's by using reference angles. So let's go ahead and get into it. First, I'm going to switch the input and the output and remove the inverse, just like we've been doing. So this is the same thing as asking the sine of what angle, and that angle has to be in the range of sine inverse, of course, equals the sine of 7 pi over 5. So we're just looking for an angle in this range where when I take the sine of that angle, it equals the sine of 7 pi over 5. So first let's draw 7 pi over 5, and let's find the reference angle of this angle, right? So if I start here at 0, it's a positive angle, so I'm going to move counterclockwise. Let's see, where am I at now? I'm at pi, but that's the same thing as 5 pi over 5. I always like to get that common denominator when you're dealing with weird denominators like this. So this is 5 pi over 5. How much further do I need to go? Another 2 pi over 5. So I'm stopping right about here. This whole angle is 7 pi over 5. And my reference angle is always the angle between the terminal side of this angle and the x-axis. So this is my reference angle. So remember, 5 pi over 5, I had to go an additional 2 pi over 5 to get to 7 pi over 5. So my reference angle is 2 pi over 5. Remember that. So now I need to find an angle in this interval that has this reference angle, okay? So let's see here. Negative pi over 2, pi over 2. So we have two angles in here with this reference angle. We have positive 2 pi over 5 and negative 2 pi over 5. But remember, whatever this is, the sine of 7 pi over 5, we know it's negative because 7 pi over 5 is in the third quadrant. That's going to give us a negative value, right? So we can again eliminate this quadrant here and focus on angles between negative pi over 2 and 0. So let's apply that reference angle of 2 pi over 5, but let's apply it between negative pi over 2 and 0, and that gives us negative 2 pi over 5. Hopefully that makes sense. I have a video covering this stuff. Theta equals negative 2 pi over 5. I have a video covering this stuff in more detail. This is tricky stuff, not gonna lie, so you gotta practice this, but hopefully that makes sense. So this example is pretty different from the last few examples in two ways. First of all, these functions are different. We don't have sine and sine inverse, tangent and tangent inverse. Now we have tangent and sine inverse, so different functions. Second of all, the inverse function is now the inner function, and the regular trig function is now the outer function, okay? So we won't expect an angle here. I'm not going to write theta because remember, the inverse functions give us angles. The regular functions give us values. So we're expecting some value out here. So what we can do with these kind of problems, I personally think they're easier than the last few problems. We can just start from the inside. We can find out what's the sine inverse of negative 1/2, right? Because that's going to give us an angle. Find that angle and then take the tangent of that angle, and that's our answer. So first let's find that angle. So the sine inverse of negative 1/2 equals some angle. Well, that's really like asking the sine of what angle equals negative 1/2. But remember, that angle has to be in the range of sine. Y'all got this down by now, I hope. Okay, so the sine of what angle equals negative 1/2, but it's got to be between negative pi over 2 and pi over 2. So here's negative pi over 2. Here's pi over 2. We can always eliminate a quadrant by looking at whether this is positive or negative. This is negative. Can't be in the first quadrant because the sine of any angle in the first quadrant is always positive. So we have to be down here somewhere. Now we got to think about what kind of angles give us 1/2 values for sine. Let's see, pi over 6 kind of angles, right? So our reference angle is pi over 6, and since we're negative and we're between negative pi over 2 and 0, we're moving backwards pi over 6. So our theta in this case is actually negative pi over 6. Theta equals negative pi over 6. Okay, so that's our angle. So this whole thing equals negative pi over 6. So we can now rewrite this entire expression as, well, that's just like asking what's the tangent of negative pi over 6. It's the same thing, right? So we've made this composition of two trig functions a lot simpler. Now we're just asking what's the tangent of negative pi over 6. So let's see, pi over 6 with tangent, that's going to give us root 3 over 3 type values. So root 3 over 3, but we are negative, so let's see, we're down here in the fourth quadrant. So we are going to be negative because tangent always gives us negative values in the second and fourth quadrant. So it's going to be negative, and we know that these pi over 6 reference angle kind of angles give us these root 3 over 3 values. So our final answer for this entire expression is negative root 3 over 3. All right, so this next example is similar to the last example. We're going to work it out the same way. We're going to start with this inner function because we know that this is going to give us some angle. So we're going to find out what that angle is and then take the tangent of that angle. So I'm going to rewrite this sine inverse of negative 2 equals theta as the sine of what angle equals negative 2. And remember, this angle has to be in the range of sine inverse. Okay, so sine of what angle equals negative 2? You may already see the problem here. What is the range of sine? Well, the sine function oscillates between negative 1 and positive 1. So is there an angle that I can plug in to the sine function to give me negative 2? No, no such angle exists. So that means this expression here is undefined, and therefore this entire thing is undefined. So always look out for that. Undefined. Always look out for when they ask you, if you end up with some kind of nonsense equation like this, and you think to yourselves, wait a minute, this is never possible? Undefined. That's a perfectly valid answer. Sometimes it happens, sometimes that comes up. So now we're back to having the inverse function as the outer function, right? We're looking at the tangent inverse of the cotangent of 2 pi over 3. So again, inverse trig always gives us angles. We're expecting to get an angle out of this. So what can we do? Well, we know 2 pi over 3. We're familiar with that. It's on the unit circle, so we should be able to easily find what the cotangent of 2 pi over 3 is, find that value, and just replace this expression with that value, and then find the tangent inverse of that value. So we're going to start from the inside and work out, okay? So 2 pi over 3, let's draw a quick sketch. 2 pi over 3 is right about there. So what's our reference angle? Well, 2 pi over 3, our reference angle we find by drawing down to the x-axis. So that's pi over 3. So what kind of values do we get when we take the cotangent of pi over 3? Well, that's root 3 over 3. So this is equal to either positive or negative root 3 over 3. That's how reference angles work. They tell us the value, but they don't tell us whether it's positive or negative. We have to determine that by the quadrant, right? So we're here in the second quadrant. Is cotangent positive or negative in the second quadrant? It's negative. So cotangent of 2 pi over 3 equals negative root 3 over 3. That's the process I use, by the way, to find the exact values when the angles are not in the first quadrant. I only had the first quadrant memorized, and I just use my knowledge of reference angles to find everything else. So if you like that, then try that. And I think I have a video on that too, explaining it a little more in depth. So since this equals negative root 3 over 3, really what we're being asked to find here is what's the tangent inverse of negative root 3 over 3. And this is still an angle that hasn't changed. And this is still just like asking the tangent of what angle equals negative root 3 over 3. And remember, this angle has to be in the range of tangent inverse, which I kind of remembered this range because it's kind of like sine, except it doesn't include those endpoints. So this range is, let's see, theta is greater than, strictly greater than negative pi over 2, and strictly less than pi over 2, okay? So our theta is somewhere in here. So let's find this angle, then we'll be done. Here's negative pi over 2, here's 0, here's pi over 2. Let's see, we have a negative value, so where is tangent negative? In the second and fourth quadrant. So we definitely got to be somewhere down here, right? So we have to be somewhere between negative pi over 2 and 0. We can eliminate that first quadrant as an option, right? So we're somewhere down here between negative pi over 2 and 0. Now we just have to kind of think about what reference angle gives us root 3 over 3 when we're dealing with tangent. And I believe that is pi over 6, right? Because the tangent of pi over 6 equals root 3 over 3. So our reference angle is going to be pi over 6. And we have to be between negative pi over 2 and 0. So we're going to use that reference angle and come back. And it's just going to be negative pi over 6, right? This reference angle of pi over 6, we use that. We come backwards since we're between negative pi over 2 and 0. And so our theta is equal to negative pi over 6. Not 11 pi over 6. Don't get it twisted. Negative pi over 6. Hopefully that makes sense. All right, so we already know that anytime our outer function is an inverse trig function, our answer we're looking for is going to be an angle. So we're looking for some angle. And we can also notice that the tangent of negative pi over 4 is something that we know. We should be able to find this pretty easily. So again, we're going to use the strategy of working from the inside out. We're going to find whatever value this is, and then find the cosine inverse of that value. So first, let's find the tangent of negative pi over 4. Maybe you already know that off the top of your head. Maybe you're faster than me. I like to write everything out just so everyone can see what it is I do and think about. So negative pi over 4, that's going to be back here, right? Because we move clockwise by an angle of pi over 4. So that's here. So we're here in the fourth quadrant, so that tells us what? That whatever this is, it's negative. And since we have a reference angle of pi over 4, we can just say, oh, well, this must equal the negative of the tangent of pi over 4, which is 1. So this equals negative 1, right? So that was pretty easy. Now we just need to find the cosine inverse of negative 1. And this is still an angle. And this is still just like asking the cosine of what angle equals negative 1. But this angle has to be greater than or equal to 0 and less than or equal to pi, because that's the range of cosine inverse. Okay, so we got to be somewhere in here, 0, pi, somewhere in this area, first or second quadrant. Well, let's think. What angle, when we plug into cosine, do we get negative 1? Well, cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. So that's it. It's pi, right? So theta equals pi. That's our answer. And I found that, the way I get that, by the way, is I know that cosine of theta equals x over r. That's the definition of cosine. So anytime x is 0, cosine is 0. Anytime x is 1, cosine is 1. If x is negative 1, cosine is negative 1. And I use that to just kind of hop around and say, okay, 1, 0, negative 1, 0, 1, 0. And all the angles that fall on that axis at that point give you that value. That's how I kind of figured out. So hopefully that makes sense. Theta equals pi. Good to go. So the way we find the exact values of these last two examples is completely different than any of the previous examples. And a lot of students struggle with these kind of problems. So I made sure to put a couple on this review so y'all can get plenty of practice. Let's go and jump into it. We're finding the exact value of this expression. Our inner function is an inverse function. So that means the sine inverse of root 2 over 3 is going to give us some angle. And then we're going to take the cosine of that angle to get our final exact value. So let's continue from here. Asking what's the sine inverse of root 2 over 3 is the same thing as asking the sine of what angle equals root 2 over 3. But remember, this angle has to be within the range of sine inverse. So greater than or equal to negative pi over 2 and less than or equal to pi over 2. Okay? So you probably already noticed the problem. This is not a value that we're familiar with. It's not on the unit circle, and we actually have no way of finding out what theta is without using a calculator, and that's a problem because it's different than anything we've done so far. But we can actually still find this exact value, because let's think about it. What are we being asked to find? Well, we're being asked to find the cosine of this sine inverse of root 2 over 3, which equals that angle theta. So really what we're being asked to find is the cosine of theta, right? So we can actually find the exact value of this entire expression, which is the cosine of theta, without ever finding out what theta is or having to know that information. Pretty cool, right? And we do that by drawing a picture and using the definitions of sine and cosine. This is stuff we've probably done in previous sections. We've definitely done this, actually. So first, let's draw a picture. We know that whatever theta is, it's definitely between negative pi over 2 and pi over 2, just based on the range of sine inverse. But this is a positive value, and that restricts us to the first quadrant. It definitely can't be down here, because this is a positive value, right? So it's got to be somewhere between 0 and pi over 2. So whatever theta is, it's in the first quadrant. Let's just say it's somewhere around here. Whatever this angle is, we'll call this theta. Now let's think about what sine tells us as a function. When we plug in an angle, we get out a ratio, y over r, or opposite over hypotenuse, right? So this root 2 is our y, and this 3 is our r. So the root 2, that's the opposite side of the triangle, root 2. And our 3 is the hypotenuse, or the r value. And what does cosine tells us? Well, cosine gives us the ratio x over r, or adjacent over hypotenuse. So really, if we're going to take the cosine of this angle, that's going to end up being whatever this adjacent side is, I'll call it x, over the hypotenuse, which is 3. So whatever this answer is for cosine theta, it's going to be something over 3, We just need to find out what x is, and we can find that using Pythagorean theorem, right? We have two sides of a right triangle. We can find the third using Pythagorean theorem, so let's go and do that off to the side here. X squared plus the square root of 2 squared equals 3 squared. The square root of 2 squared is just 2. 3 squared is 9. Now I'm going to subtract 2 from both sides and then square root both sides. I'm going to do 2 steps at once, but I know y'all can handle it. Okay, and that gives me x equals square root of 7, but is it plus or minus, right? Because remember, when I square root, I have to put a plus or minus there. Well, in this case, we're in the first quadrant, so whatever our x value is, it has to be positive. So in this case, it is positive, and that means our final answer is the square root of 7 over 3, but make sure to pay attention to that, because you will get some tricky problems where you'll have to put a negative there based on which quadrant this is in. So pay attention to that. But hopefully this makes sense. Let's go and do the last example. All right, so this is the last example where we're going to find these exact values. Let's go and jump right into it. This is the expression we're looking to find the exact value of. We can notice that the inverse function is the inner function in this case. So the sine inverse of negative 1/3 is going to give us some angle, and then we're going to find the tangent of that angle, and that's going to give us this final exact value of this entire expression. So we're going to do the same thing we did in the last problem. We're going to start from the inside function and work our way out. So asking what's the sine inverse of negative 1/3 is the same thing as asking the sine of what angle equals negative 1/3. But of course, this angle has to be within the range of sine inverse. So from here, we come across the same sort of problem that we had in the last example, where this is a value that we are not familiar with. It's not on the unit circle, and we have no way of finding out what this angle theta is without using a calculator, but we can still use our definitions of sine and tangent and draw a picture to find what the exact value of this entire expression is. And we do that because we know that the sine inverse of negative 1/3 is going to give us this angle, and then we're going to take the tangent of that angle, and that's going to be this final exact value. So again, this is our angle, so really what we're looking to find is the tangent of theta. So just remember that. If you ever get stuck, always ask yourself, wait, what exactly am I trying to find again? And go back to the original problem and remind yourself that we're really just trying to find the tangent of theta. We don't need to actually find theta, we just need to find the tangent of theta. So let's draw a picture. We know that our angle theta is for sure within this interval between negative pi over 2 and pi over 2. But since this is a negative value coming from the sine function, we can isolate this. We can definitely say that this is within negative pi over 2 and 0, somewhere in this fourth quadrant. We know that because sine is always positive up here in this first quadrant, right? So we can definitely narrow it down to this fourth quadrant between negative pi over 2 and 0. And now we can draw our angle theta. Whatever it is, it's in the fourth quadrant down here. We can draw it. This is theta. Now we use the definition of the sine function. Remember, sine takes in an angle and it spits out a ratio. And that ratio is y over r, or opposite over hypotenuse. So in this case, if we draw a triangle, our opposite side is going to be negative 1, which makes sense because all of our y values are negative down here in the fourth quadrant. So it makes sense that that negative 1 corresponds to the y value. Our r is 3. And now let's remember what we're trying to find. We're trying to find the tangent of theta. What ratio does tangent give us? Well, we plug in an angle and it spits out y over x. It's really important that you know those definitions of these trig functions. So y over x, or in other words, let's see, SOHCAHTOA, TOA, opposite over adjacent, okay? So whatever this tangent of theta is, it's going to be opposite, so negative 1 is definitely in the numerator, over adjacent, which is this angle here. We'll call it x. We don't know what it is, but we can find it using Pythagorean theorem. So as you can see, it's exactly like the last problem, the previous one, as far as the process, just the numbers are different, the quadrant is different, we have a different function here, but it's always the same process, okay? Draw your picture, figure out which quadrant it's in, figure out which side you need to find, and then use Pythagorean theorem to find that side. So that's what we're going to do right now. We use Pythagorean theorem off to the side here. X squared plus negative 1 squared equals 3 squared. So I can write this as x squared plus, let's see, negative 1 squared is just positive 1. 3 squared is 9. So if I subtract 1 from both sides and then square root both sides, I end up with x equals the square root of 8. And now remember, when we square root both sides, we normally write a plus or a minus. But I can determine whether this is positive or negative based on whichever quadrant theta is in. Since we're down here in the fourth quadrant, all of our x values are positive, so therefore this is indeed positive square root of 8. And we can even go a little bit further and we can sort of break this down into 2 root 2. And it depends on what your instructor is expecting you to do. I'm going to do it for the sake of this video, but we can, you know, write this as 4 times 2. And we know that the square root of 4 is 2, so we can pull that out. And this becomes 2 root 2. Okay, so this is our final answer. Tangent theta equals -1 over 2 root 2. But we can go and again do something else to make this a little bit cleaner, because a lot of times we don't like these radicals in the denominator, so we do something called rationalize the denominator. So again, it's really up to how picky your instructor is, whether they want you to break this down, whether they want you to rationalize this denominator or not. But I'm gonna go ahead and do it for the sake of this video. So what we do when we rationalize the denominator is we multiply by root 2 over root 2, because that gets rid of the radical in the denominator. And when I take this and multiply by root 2 over root 2, let's see, I get -1 times the square root of 2. So that's, I'll write it up here for our final answer. That's negative root 2 over 2 times the square root of 2 times the square root of 2. Well, these two square root of 2's, that square root sort of cancels, right? Square root of 2 times square root of 2 is just 2. And 2 times 2 is 4. So we end up with negative square root of 2 over 4. So again, based on the instructions of your instructor, whether they want you to do this process or even this process, it's really up to them. But I showed it all because they most likely want you to do all of this. But this is our final answer. Hopefully that made sense.
The next day.
All right, so for number 2, we are given a function. We're asked to find the inverse function of this function as well as the domain of that inverse function. So typically when we find inverse functions, we switch the x and the y, and then we solve for that new y. That's exactly what we're going to do here. So I'm going to switch the x and the y, so I can write this as x equals 2 cosine of 3y plus 2. And now I have to solve for that y. The problem is that y is inside this cosine function. So what I need to do is I need to isolate that cosine. So get everything else on the other side of the equation, get this cosine piece by itself on this side of the equation, then I can take the cosine inverse of both sides. So in this case, all we need to do is divide both sides by 2 to isolate this. But if there was like something being added or subtracted out here, I would move that over first, then divide, or do whatever you need to do, but always isolate that cosine piece. So if I divide both sides by 2, I get x over 2 equals cosine of 3y plus 2. Now I've isolated the cosine part of the equation, and now I can take the cosine inverse of both sides. So when I do that, I get cosine inverse of x over 2 equals, and remember, cosine inverse of cosine, those cancel. That's why I applied the cosine inverse to both sides, to get rid of this cosine and get this 3y plus 2 expression out here by itself so I can solve for y. Remember, that was the whole point of using cosine inverse, was to get this y out here so I can solve for it. Now all I need to do, I'm going to do 2 steps at once, but I think I can handle it. I'm going to subtract 2 from both sides and then divide both sides by 3. And by doing that, I get y equals, and that's going to be my inverse function, right? So if I subtract 2 from both sides, I get cosine inverse of x over 2 minus 2 equals, remember that equals 3y, so I also have to divide both sides by 3. So what I can do is I can just put a big bar here and put all of this over 3. I can write each one individually over 3. I may just write a 1/3 out in front and put parentheses. I think that's what I'll do here, just to save a little room down here. So this is our final inverse function. This is the inverse function of this original function. And how can we check our answer? Well, I can plug this function into this function, and what should I get left with? Just x, right? When you plug an inverse function into the original function, it spits out x and vice versa. So that's one way you could check your answer, but I'm pretty confident that this is good and we don't need to do that here. Now we just need to find the domain of this inverse function. And there's 2 ways to do this. If we understand the relationship between a function and its inverse, we know that the domain of this inverse function is the same as the range of the original function. So we can either find the range of this original function, because we know that's going to be our domain, or we can just directly find the domain of this inverse function. Either way works. I'm going to go ahead and do both. So finding the range of the original function in this example especially, I think is actually easier, especially if we already know how to graph these guys, which we should have already learned by now. But I know that the amplitude of this function is 2, and there's no vertical shift. There's nothing being added or subtracted out here. So we're going to go from 0, our maximum is going to be 2, and our minimum is going to be -2. We're going to oscillate about that midline 0 all the way up to 2 at its maximum and -2 as its minimum. So the range of this is that closed interval let's see, range is the closed interval from -2 to +2, and that should also be the domain of this inverse function, but we can double check that as well. So to find the domain of an inverse function, we have to understand what the domain of the parent function is. So let's think about what the domain of something like this is. Y equals cosine inverse of x. Well, remember, this inverse function takes in values and spits out angles, right? So it can't take in values bigger than 1, and it can't take in values less than -1. So the domain of this original inverse function is the closed interval from -1 to 1, right? Because that's the range of the parent function, y equals cosine x, right? So the range of this is the domain of this. So that means that even though we have an x/2 here, whatever is in this entire argument, because that's what's inside this cosine inverse function, whatever is in this entire argument has to be in that closed interval from -1 to +1. That means that -1 has to be less than or equal to x/2, which has to be less than or equal to +1. And now we can solve this inequality by multiplying everything by 2, and we'll end up with -2 less than or equal to x less than or equal to 2, which lines up exactly with what we got from the range of the original function with the domain of the inverse function. So this means that the domain is the closed interval from -2 to 2. So whichever way you like. I personally like finding the range. I think that's easier. Find the range of the original function. We know that that's the same thing as finding the domain of the inverse, but you can do whichever method you prefer. They should give you the exact same answer. All right, so now we're going to review the last topic being covered in this video, which is solving trig equations. So we're going to do a bunch of examples, starting from fairly simple like this one and progressively getting harder. And I hope this helps y'all review. So let's go ahead and get started. Our general strategy is going to be to isolate the trig piece of the equation. So I want to get sine theta equals something. That's going to be my strategy. And then from there, I can figure out what angles sort of work with that equation. And you'll see what I mean in just a second. So to get sine theta by itself, I need to subtract 1 from both sides. That's the first thing I need to do. So if I subtract 1 from both sides, that +1 goes away, and I have -1 over here on the right side of the equation. Now I need to divide both sides by 2 and get rid of this 2 out here in front of that sine theta, okay? So if I divide both sides by 2, now I have sine theta equals -1/2. And now there's different ways you can go from here. I've seen some people actually take the sine inverse of both sides. I don't like that method, and the reason why is because I feel like you have to do a lot of extra work. You know, a lot of times when students do that, they really rely on certain formulas to get their answers. I think it's better just to think about the unit circle, right? Think about the unit circle and think about what angles make this work. What angles can I plug into sine that are between 0 and 2 pi? That when I plug those angles in, I get out -1/2. Well, we for sure know that since we're dealing with sine and we have a negative value, if we're between 0 and 2 pi, then we got to be down here in the 3rd and 4th quadrant, because those are the 2 quadrants where sine gives us negative values, okay? And if we know a little bit about reference angles, we can think about, well, what angles give me 1/2? Let's see, I believe that's pi/6. So if we take that pi/6 reference angle and we apply it down here in both of these quadrants, we can get both our solutions on this interval. And remember, that reference angle means that that's the angle between the terminal side of the angle and the x-axis. So this is pi/6, and this is pi/6, okay? Which means that this angle is going from 0 all the way to, let's see, that would be like 6 pi/6, 7 pi/6, right? We're going a full pi and then an extra pi/6. So 7 pi/6 is one of our solutions. What's our other solution? Remember, we're not going to negative pi/6. That's not within this interval, right? So we're not going backwards. We have to go forwards. We're going to go all the way around, and we're going to stop pi/6 short of a full 2 pi revolution. So that's one way you can think about it. You can take 2 pi and subtract pi/6, and if you do that, that's going to give you 11 pi/6. So hopefully that makes sense. We're finding the reference angle that gives us the value based on whether it's positive or negative. We're figuring out which quadrants we need to be in, and then we're just, you know, I would always draw a picture, especially when you're first learning this. As you get better, you probably won't need to, but I always do it just so y'all can see my full kind of thought process around this. So we have 2 solutions, right? 7 pi/6 and 11 pi/6. So typically I'll write theta equals, and I'll use these curly brackets, and I'll write my solution set here. 7 pi/6, comma, 11 pi/6. So we're going to approach this problem the same way we did the last problem, which is what we're really trying to do is isolate the trig part of this equation. So we want to get that cosine piece by itself on one side of this equation. And we can do that by first adding 3 to both sides and then dividing both sides by 4. So that's exactly what we're going to do. We're going to first add 3 to both sides of this equation. That gets rid of that minus 3 on the left-hand side and leaves us with 4 times cosine squared theta equals 3. Now if we divide both sides of this equation by 4, we get rid of that 4 out in front of the cosine squared, and we get cosine squared theta equals 3 divided by 4. So it may seem like we've isolated the trig part of this equation and we're good, but what we really want is cosine theta equals something. Now we have cosine squared theta equals something. So we need to get rid of that squared, and we can do that by taking the square root of both sides of this equation. But don't forget this really important step. A lot of students forget this. Don't forget, when you take the square root of both sides of an equation like this, you have to put plus or minus. You have to do that. And the difference between doing it and not doing it could be the difference between getting this question fully correct and half correct. And you'll see what I mean at the end when we find our solution. So now what I have is cosine theta, right? That square root got rid of the squared. Cosine theta equals plus or minus. And what I'm going to do now is split up this square root, right? I'm going to write this as the square root of 3 over the square root of 4, which is just 2. And now you probably can see why I split that square root up, because this is a value that we're very familiar with. It's on the unit circle, and we can definitely work with this value, okay? So really what we're looking for are angles in this interval between 0 and 2 pi, where when we take those angles and plug them into our cosine function, we get either positive root 3 over 2 or negative root 3 over 2. So let's draw a little picture here, and let's think about what kind of reference angle we're dealing with. Well, I know that the cosine of pi over 6 is root 3 over 2. So that's going to be our reference angles, pi over 6, okay? So this is our reference angle here. And now let's think about where cosine is positive and where it's negative. Cosine is positive here in the first and fourth quadrant, and negative here in the second and third quadrant. But remember, we're looking for where this is plus or minus root 3 over 2. So we can be in any of these 4 quadrants, right? Positive or negative. So we want to take this reference angle and apply it to all 4 quadrants. So that means I need a pi over 6 here, a pi over 6 here, and a pi over 6 here. And now I need to find all of these angles. So we know that the first one is pi over 6. Let's go ahead and start writing out our solution set. The first one is pi over 6, and that's actually our reference angle. What's the second one here? Well, we're stopping pi over 6 short of pi. So that means we're going to end up at 5 pi over 6. So it's 5 pi over 6. Our third one, we're going pi over 6 past pi. So we can take pi and add pi over 6 to get 7 pi over 6. And our last one, we're stopping pi over 6 short of a full revolution, a full 2 pi. So that's going to be 11 pi over 6. 11 pi over 6. So now think about if I had forgotten to put plus or minus and just taken the positive values, I would have just ended up with pi over 6 and 11 pi over 6. So I would have missed 2 of the 4 possible solutions. So make sure to remember that plus or minus. Don't forget that part. So in this example, we already have the trig part of the equation isolated for us, right? The only thing that's different is we have this theta over 2. And what I call this is the argument for the trig function, right? Whatever's inside the function. So instead of theta, we have theta over 2, and this is going to come up a lot. We're going to see 2 theta. We might even see 3 theta or like 2 theta over 3, some weird stuff. But you're going to have to be comfortable with solving these kinds of equations. So I'm going to show you the way I do it, and I understand there are different ways to do it. So if you have a way that works and we get the same answer, that's perfectly okay. But what I like to do is first I like to look at the interval theta is in and find the interval that the argument has to be in. And what I mean by that is if theta is greater than or equal to 0 and less than 2 pi, then where is theta over 2, right? What interval does theta over 2 have to be in? Well, I can find that by just dividing everything by 2, right? So 0 divided by 2 is just 0, and 2 pi divided by 2 is just pi. So since theta is greater than or equal to 0 and less than 2 pi, theta over 2 is greater than or equal to 0 and less than pi. So instead of doing a full revolution like we normally would if this were just theta, we're doing half a revolution. And you're going to notice that in general, when we have theta over 2, we have less solutions that we end up with, and we have 2 theta and 3 theta and stuff like that, we have more solutions. Because if we solved for 2 theta, which we'll do in the next problem, so I'm kind of jumping ahead here, but I want to make this connection. If we solved for 2 theta, we'd end up being between 0 and 4 pi, doing 2 full revolutions, so we'd end up with more solutions. But that's something that's good to notice, because you want to be able to look at this and have an idea of what you're going to end up with. That's always helpful. So now let's look at this interval from 0 to pi, and let's think about what angles, when we take the tangent of those angles, do we get negative root 3 that are between 0 and pi, right? So first of all, we notice the negative here, so we can definitely rule out the first quadrant, because tangent's always positive here. So we're definitely in the second quadrant. Now let's find our reference angle. Well, let's see what reference angle gives us root 3 when we're dealing with tangent. I believe that's pi over 3. And whatever method you have for finding that angle, that's fine. Or maybe you jump straight to the 2 pi over 3 angle. That's fine too. So pi over 3 is our reference angle, which means that the actual angle itself is 2 pi over 3. So 2 pi over 3 is what? Let's think about this for a second. The tangent of 2 pi over 3 equals negative root 3, right? So when I take this theta over 2 and replace it with 2 pi over 3, I get a true equation, a true statement, right? So this is not a solution for theta, it's a solution for the entire argument, theta over 2. So a lot of students make that mistake and they write, oh, theta equals 2 pi over 3, done. But this is a solution for theta over 2. And now we can solve for theta really easily by just multiplying both sides by 2. So if theta over 2 equals 2 pi over 3, then theta equals, let's see, multiply both sides by 2, 4 pi over 3, right? And this is my one solution for this equation. And if you don't believe me, maybe you think there are more solutions, you are welcome to try. Maybe you're thinking, well, the tangent of 5 pi over 3, right, this angle here, is also negative root 3. How come that doesn't work? Well, let's see. 5 pi over 3, if that were a solution for theta over 2, then what would happen? When you multiply both sides by 2 and you solve for theta, you're going to end up with theta equals 10 pi over 3, which is outside of this interval, right? So doing this and finding that interval for whatever the argument is actually kind of does that work for us. We don't need to guess, or we don't need to think about, well, are there more solutions? We already know that all the solutions for the entire argument itself are going to be on this interval. So that's why I like this method. Hopefully that makes sense. Now in this example, we see that, again, we have the trig part of the equation isolated for us, but this time instead of theta over 2, we have 2 theta. So I already talked a little bit about what we can expect from this type of equation, but let's go ahead and solve it the same way we did the last one, which is first we're going to look at this argument, 2 theta, and find the interval that 2 theta needs to be in. In other words, theta needs to be greater than or equal to 0 and less than 2 pi. So what does 2 theta need to be between? Well, we can find that by multiplying everything by 2. So 0 times 2 is still 0, and 2 pi times 2 is 4 pi. So again, instead of doing 1 revolution, we're doing 2 full revolutions. So what we can do is just look at 1 revolution, find all the solutions, right? All the angles where the cosine of those angles equals negative 1/2. Find all those angles on 1 revolution, and then take those angles and add 2 pi to each of them to get the other angles. Hopefully that makes sense. So let's first look at where cosine is negative. So we're looking at the second and third quadrants, because that's where cosine is negative, over here. And now let's think about what reference angle gives us these 1/2 values with cosine. And that should be pi over 3. So pi over 3 is our reference angle in the second and third quadrants. So that means we are here and we are here. So using those reference angles, we can find that these angles themselves are 2 pi over 3 and 4 pi over 3. So those are 2 of our solutions. 2 pi over 3, 4 pi over 3. But again, we're doing 2 full revolutions. So I could take each of these angles and add 2 pi to them to get the other 2 solutions. So if I add 2 pi to this angle, let's see, 2 pi is like what? You can get common denominators to make it easier for you. 2 pi is like 6 pi over 3. So that would be 8 pi over 3 and 10 pi over 3. I'm running into this graph a little bit. So these are all four solutions for what? Not for theta. Remember, they're solutions for the argument, right? Because if I replace 2 theta with any of these, it's a true equation, right? It's a true statement. So these are all solutions for 2 theta. So to find all the solutions for theta, I just take every single one of them and divide by 2, okay? So theta equals, and we have all 4 of these solutions, but we divide each one by 2. So this one, if we divide by 2, these 2's will cancel. We'll end up with pi over 3. This one, if I divide by 2, let's see, 2 goes into 4, so I'm going to end up with 2 pi over 3. This one, let's see, 2 goes into 8, so that's going to be 4 pi over 3. And this one should be 5 pi over 3. And you can see that all of these are within that 0 to 2 pi. And if you go back and plug each one of these in, you'll see that they will end up being true, right? Because once I plug this in for theta, it gets multiplied by 2, and I have the cosine of 2 pi over 3, which we already know is -1/2. And you can check your answer for each of these, but these are all 4 of the solutions for this equation. All right, guys, this is the last example in this review. If you made it this far, I hope you got something out of it. I will be doing a part 4. I don't know when I'll be doing that, but pretty soon I should be doing a part 4. The reason I wanted to give this example for solving this equation is because this is an example of when we can't just isolate the trig function, right? We can't just get cosine theta equals something, because here we have a cosine squared term, here we have a cosine term, so what we really have to do is factor this. We have to sort of treat it like a quadratic, right? And if you don't see that it looks kind of like a quadratic, just replace cosine theta with x, right? This would be 2, let's see, cosine theta, if we replace it with x, this is like 2x squared. And this is like x equals 0. So if you know how to solve something like this, then you should be able to solve something like this, right? To solve something like this, we would factor out an x, and then we would go from there. So that's exactly what we're going to do up here. So we're going to factor out a cosine and go from there, right? But every time I show that, you know, writing it as x, a lot of students are like, oh, I see it now. So that's why I like to do that. So if we factor out a cosine, then we're left with 2 times cosine theta plus 1. Okay, and now again, we treat it like a quadratic. So we have it fully factored. We have 2 things being multiplied. So that means we're going to set this equal to 0 and this equal to 0 and solve each trig equation. And the solution to each of those, right, those solutions together will be our final solution set for this original trig equation. Hopefully that makes sense. So we set cosine theta equal to 0. And we're going to find the values for theta that work for this equation on this interval, and we're also going to do this equation as well. 2 cosine theta plus 1 equals 0. So first let's start with the easy one. Where does cosine equal 0? Well, cosine is the x, remember? X over r. So whenever x is 0, cosine is 0. So x is 0 up here at pi over 2 and down here at 3 pi over 2. So those are our 2 solutions for theta from this equation. I'll just make a note of it over here. Pi over 2 and 3 pi over 2, right? So those are our 2 solutions from this first equation. Now the second equation, now we have to take this equation and do kind of like we did in the previous ones, which is isolate the cosine. So subtract 1 from both sides and divide both sides by 2. So if we do that, I'm going to do both steps at once. I believe in y'all though. Y'all can handle this. Quick math. So subtract 1 from both sides, then divide by 2. We get cosine theta equals -1/2. Now we're going to find the solutions for theta for this equation, and then we're going to take both of those solutions together, and that's going to be our final solution set. So for -1/2, since it's a negative value, it's definitely in the second and third quadrants, right? These angles that work with this equation. And let's think about the reference angle that gives us those 1/2 values with cosine. That's pi over 3, right? So we have a pi over 3 angle here and a pi over 3 angle here. And that means that each of these angles are 2 pi over 3 and 4 pi over 3. Those are 2 solutions to this equation, 2 pi over 3 and 4 pi over 3. So if we combine all these solutions together, that makes our full solution set for this original equation. So we have pi over 2, and I'll write theta equals, and I'll do the curly bracket here, pi over 2, 3 pi over 2. And then what were these two again? 2 pi over 3 and 4 pi over 3. 2 pi over 3 and 4 pi over 3. Those are our final solutions for this original equation. So anytime you see cosine squared and cosine, just think, oh, this is like a quadratic, right? And if you have to replace those with x to kind of see what you're going to end up doing, do that, that's fine. Sometimes you may even see them throw a sine squared in. You have to use an identity to change that into a cosine squared and then combine terms. Those are even trickier. Last thing I want to say before I wrap up this video, I solved all of these equations on this interval. Sometimes you'll be asked to find all possible solutions. So when you do that, typically what you do is you find them on this interval, and then you just write each one plus 2 pi k, where k is any integer. But the process is essentially the same, but if you want, I maybe will make a video focusing on that, just a quick one, and do a couple of examples. If you want to see that, let me know in the comments below. But I hope you all enjoyed this video. Hope you all enjoyed. This takes a lot of time to make these long kind of videos like this. I have to prepare and film, and I do multiple takes, and I got to edit and do all that stuff. So if this did help you out, make sure to hit like, leave a comment below, letting me know what you got out of this, and hit subscribe. But most importantly, keep flexing those brain muscles. See y'all later.